What we're going to be looking at, so far, Josh, we've looked at static electricity, which is what happens if we put electricity on an insulator and don't let it go anywhere. Although when we touched it with ourselves, because we're a okay conductor, we get a shock. What we really want to ask ourselves now is, well, I mean, shocks are fun, and the static stuff was cool. You could make things move, and you could get a balloon to stick to a wall, but that's not useful. How, Brooke, do we have our whole electric infrastructure? How do we make electricity run stuff? And I mean, you can get a doctorate in that and do 10 years of study. We're only going to look at the very basics of it. But Jaden, what I am going to do actually is sneak a bunch of Physics 12 into here, because you guys are doing pretty good on this. I'm actually going to teach you folks how to solve circuits, how to analyze a circuit, basic ones, not with all sorts of fancy schmancy components, because that you can get into electronics and again do that for 10 or 15 years. But we have to start out with some definitions, and what we're going to talk about today, how batteries work. So we got to have some definitions. First of all, Coulomb. What's a Coulomb? A Coulomb is a unit of electric charge. A unit of electric charge. Oh, got someone coming in late. Pause. Under nerd trivia, I think I told you 1 Coulomb is an awful lot of charge. If you absorbed 1 Coulomb all at once, Brian, it would probably stop your heart and kill you. A lightning bolt has about 15 to 20 coulombs, so 1 Coulomb is huge. Or if an object gains 6.25 times 10 to the 18th electrons, if an object gains a 6, a 2, a 5, and 16 more zeros, that many electrons, I have no idea how big a number that is, it gains 1 Coulomb of charge. Another term we're going to use is the term potential. Potential is the ability to do something. We might say something like, Mason has the potential to be on time. I would be saying that he has the ability to be on time. Right? Mm-hmm. Another term, energy. Energy is not, oh, I've got some sugar and can't sit still. In physics, energy has a very, very specific definition. Energy is the ability to do work. Now, in physics, work has a very specific definition. If you take Physics 11 or Physics 12, you'll learn that work is actually a force times a distance. It's the ability to apply a force over a given distance and make something move, but we'll get there. So I wrote down here, energy is the ability to do work, make something move, make your iPod work, etc. Now, there's something called the law of conservation of energy. It says this: energy cannot be created or destroyed. It can only change form. We can't make energy from nothing. What we can do, though, is we can store it in a battery and then bleed it off slowly to run an appliance, to run a flashlight, to run a smartphone. There are many types of energy, but we can break them into 2 main categories. There's what we call potential energy. This is energy that's stored in an object. And then there's something called mechanical energy. I'm not going to get into that, but that's energy that's causing something to move. There's different types of stored energy. Electric potential energy is stored electrical energy. So batteries contain, what's E minus my symbol for? Okay, batteries contain electrons that are, and I put the word released in quotes, they're not moving around quite as much as we think, but I'm not going to get into the details. But a battery contains a bunch of extra electrons. It's got electrons that want to repel each other, and we don't let them repel each other through the battery. We make them repel each other by going through a circuit. And as they're moving through a circuit, we can bleed some of that energy off and get it to power something. So when you turn your iPod or whatever on, the energy that can contain is converted to heat or light or sound, etc. So this gives us what we call an electrochemical cell. That's the fancy name, Mason, for what we call a battery in everyday life. Actually, a battery is a bunch of electrochemical cells put together. The word battery actually comes from an old artillery phrase. When you had a bunch of cannons together, you called that a battery. When you have a bunch of cells together, you call that a battery. We're used, Trevor, to saying that's one battery, but actually if you took that battery apart, you would find inside that one battery many cells, many little electrochemical cells. And again, these store chemical energy that can be converted to electrical energy. Inside a battery, there's a chemical reaction that contains chemical energy, and by being clever, we can change that into electrical energy, into moving electrons. You might recall near the beginning of the year, I said something like, it's the electron, stupid. Everything, Grace, all the interesting stuff on the periodic table, it's really going on with the electrons for the most part, because they're on the outside and we can move them around. So a battery is a series of electrochemical cells connected together so that you can supply more power. The chemical reaction, the typical chemical reaction that we use in a battery in one cell doesn't give us much voltage, but if we link them together, yay, we can get 1.5 volts out of there. We've got a battery. What's a volt? We'll get there. So here's a little thought question. What do you think has more stored energy? What do you think has the ability to do more work? A tennis ball 2 meters above the ground? A bowling ball 2 meters above the ground? A tennis ball 20 meters above the ground? Or a bowling ball 20 meters above the ground? And I wrote here, ask yourself, which one would hurt more if it hit me? So our little thought experiment, we pause the video. That one there. In physics, we say, here's the physics version of that same question, Nick, which one could do more useful work? So when we're talking about physical objects, I guess the amount of stored energy depends on two things. How high it is and how heavy it is. Let's write that formally. Potential energy due to gravity depends on two things. It depends on the height of an object, and it depends on the mass of an object. Is that okay, Hannah? So the heavier an object and the higher you lift it, the more energy you stored in that object, because when you let it go, it'll do some work. It'll do some damage. Or if you don't want it to do damage when you let it go, you can have it power a machine, for example. A great example of that, if you have an old grandfather clock in your house, there's weights in there. The way you wind that clock is you actually lift those weights up, and they very, very, very slowly lower, and that's what powers the clock. You can use that for useful work. So how high, how heavy? Well, in electricity, Martin, there's a very, very similar concept. It's not height and mass, because that's not what we're talking about with electrons. It's called voltage. This is my analogy, Trevor. When I look at a battery, if I see a 9-volt battery versus a 3-volt battery, what I'm thinking to myself, that 9-volt is sort of like the bowling ball raised up high. The 3-volt is like a bowling ball not raised so high, or a tennis ball not raised so high if it's a 1-volt. So a higher voltage battery has more stored energy. Is that okay, Matt? Okay, we're going to get into some detail here. So section 8.1, this is from key ideas from our notes, from our textbook. Energy is the ability to do, anybody remember what I said earlier? Work. That's the physics definition. There are two main types of energy. One of them is called kinetic, Kinetic, and this is the energy of motion. In other words, any moving object has kinetic energy. So, I'll pick on Mason because he came late. Mason, if I were to throw this tennis ball and hit you in the face, would it hurt? Would it do some work? Yes, because it has some energy. What if I threw it faster? Hurt more or hurt less? More energy or less energy? More. What if instead of a tennis ball, I threw my lead fishing weight? Okay, it turns out, and you've just sort of derived this intuitively, in physics we learn motion energy, kinetic energy, depends on how fast and how heavy. Okay? Sadly, we won't do that experiment. Then there's potential energy. This is energy that's stored in an object. It has potential. It has the ability, but it hasn't yet done the work. A good example is the water behind a hydroelectric dam. It has gravitational potential energy. We let the water pile up, and really what we're doing that is we're letting most of the water raise itself to a height, the same way I lifted that fishing weight up to a height, and then we have a hole in the bottom of the dam. We drain the water through there, and it can turn a turbine. We can get it to do some work. Batteries contain stored energy called electric potential energy. More energy than you probably realize. Put your pencils down. So, oh, he's still here. Just moved over one. Wait, Nick, like charges, repel, unlike charges. So, when unlike charges are moved further apart, they gain electric potential energy. It's sort of like lifting a big heavy mass. Nick, unlike charges, what? Attract. It turns out gravity, mass attracts other mass. It's not like unlike charges, but mathematically it's similar. This mass is attracted to the mass of the Earth. And the further I move them apart, the more stored energy I put into this mass. The further I move apart, unlike charges, the further I separate charges, or Martin, to use a physics term, the more work I do in separating charges, I store more energy. Or you can kind of think of it like stretching a spring or stretching an elastic. It gives it stored energy, and when you let it go, you can do something with that energy, run a little toy plane or whatever, or like lifting an object to a height. In a battery, the unlike charges are blank and protons. Hey, what are the unlike charges? Electrons. Can I use my little symbol? Sure. Electrons are removed from one end or one section of the battery and sent to the other. And that creates electric potential energy due to charge separation. The same way as lifting that fishing weight up high creates gravitational energy because I've separated two masses and that weight wants to fall back down. Can I say, and this is kind of wrong, but it will kind of, the electrons want to fall back down to the protons. They're not falling, but same analogy. Is that okay? And again, the further you separate them, the more you separate them, the more they want to fall back down. The unlike charges, Nick, attract each other. Sort of like how when we lift something, it wants to fall back to the earth. So let's get more specific with some terminology here. If we're talking about charge separation, you've seen batteries, you put them into devices. They don't all look like this. The ones inside your phone are flat and rectangular because we like our electronic devices to be thin. But basically, Brian, every battery has certain things in common. First of all, they have terminals. These are the endpoints of a battery where we can make a connection to a circuit. So on one terminal, we have extra electrons accumulated. If you have extra electrons, what charge will you have? Are you positive about that? Negative. That was funny. No. The other terminal, now we can't move protons around, but we can lose electrons. And if you lose electrons, what would the charge be? Are you positive? Yeah, okay. Come on. So before you turn the page, I don't know if I included these pictures in your notes, but so in a standard one of these types of batteries, that little round dot is the positive end, the bottom is the negative end, although really inside it's not quite, it's actually separated through the center, but I'm not going to get into that. Here in a car battery or a big flashlight battery, one of these will be a positive terminal, one of these will be a negative terminal, and they'll be labeled. A circuit. I don't think I have this in your notes. I'm just giving you some pictures. So a standard circuit will have a wire going from one terminal through some kind of device to bleed off the energy, connecting to a switch if you want to be able to turn it on and off, and then ending up with a wire that connects to the other terminal. We call this, here's your fancy word, a closed circuit or a closed loop. If a circuit isn't closed, it won't run. If you don't have a closed loop, there's nowhere for the electrons to flow. Batteries. To make a battery, what do you need? If you were to take apart, let me pause the video for 1 second. I don't have my props ready, Mr. Dewick. That's silly. If you were to take apart a battery, what would you see inside? By the way, don't take apart batteries without eye protection and gloves because there is a mild acid in here, and we'll see why in a little bit, but there isn't acidic paste. Don't take apart a bigger battery like a car battery or one of those big square flashlight batteries at all unless you really know what you're doing. Like if you have a parent who's an electrician or something like that and you're doing it with their supervision, that's one thing. But don't muck around with batteries too much. There's some nasty chemicals in there. But if you did take one apart, what would you see? Well, to make a battery, we need two different metals as terminals, or fancy word, electrodes. Why two different metals? One of them will be hungrier for electrons than the other one, and so we will get the ability to pull electrons from one metal to the other one. Why metals? Because metals are very, very willing to allow electrons to travel through them. Just touching two metals together can generate a very, very small voltage and generate a current, but we can improve this. So usually what we do is we have something that we call an electrolyte, L-Y-T-E. This is usually an acid or alkaline paste, something pretty thick, technically still damp or wet, but barely. And what that does, it allows electrons to flow from one terminal to another, as opposed to trying to go through air. Air is not a good conductor. As opposed to having them touch directly, that would bleed things out too much. We want to be able to regulate the flow. So Energy stored inside a battery is called, I've repeated this, which means it's probably going to be on your next test because it's important. It's called electric potential energy. Stored potential. What kind of energy? Electric, so electric potential energy. Stored by the position of the electrons. When you stretch an elastic band, you're storing energy. When you release it, you're releasing the energy when you let go. The more you stretch the elastic band, the more energy you store, and the more it will hurt when it hits your hand and you let it go. Let's keep that in the back of our mind. We're going to talk about voltage. Voltage is a tough concept to wrap our brain around. What is it? I mean, it's a number, but what does voltage actually mean? Another word for voltage is the word potential difference, and we'll talk about what that means in a bit as well. What's the definition? It's the amount of electric potential energy per Coulomb of charge. Spell Coulomb right, Mr. Dewick. There's a U in there. Can you, Brady, read to me the voltage on this battery? Grab it. Read it. Nice and loud to them. 1.5. 1.5 what? Okay, here's what that means. It means that every Coulomb of charge in that battery has 1.5 joules of energy. 1.5 volts is 1.5 joules per Coulomb. Now, you don't know what a joule is. You sort of know what a Coulomb is. Really, it's a way of saying how much energy each charge has. Higher voltage means each charge has more energy. Doesn't necessarily mean you have more charges, just means each one of them has more energy. So a 9-volt battery, each charge has more energy than a 1.5-volt battery. Is that okay, Matt? Okay. So it's really related to how much energy each electron has. Another word for voltage, which initially is confusing, but if you get into electronics actually starts to make more sense. Voltage is also called potential difference. So what? What you really want is a difference in voltage between two locations in a circuit, a potential difference. Then charges will flow. If you have two areas in a circuit at the same voltage, that's like having a flat plateau on a mountain and you've raised the objects there, but because that area of the mountain is flat, there's nowhere for them to roll or do work. You want a slanty hill where there's a difference in height and the things can drop down. In fact, the analogy, Grace, that I'm going to start to use for voltage, I'm going to say voltage is sort of like how high a ski hill is. The higher the voltage, the higher the chairlift you went up. And what you really want in order to get down the ski hill is a difference in height, a potential difference, a difference in voltage. How do we measure voltage? We use a device called a voltmeter. And it measures the potential, or you can put in brackets, voltage difference between two locations. We'll play with some voltmeters probably next class, well, after the test. Mason, anybody here ever used a voltmeter to measure a circuit? You have? So what you have, every voltmeter has two leads, and what you have to do is you have to touch it to one area of your circuit, touch it to another area of your circuit, and really it's measuring the difference in height, the difference in voltage, the potential difference between the two. You can't measure voltage by only touching one area. A voltmeter wants to know what's the change in voltage, what's the difference between those two areas. What's a voltmeter look like? We'll play with them in a bit. So potential energy is a battery of a battery. What I'm going to say to you, because Hannah, voltage is a tricky concept to wrap your brain around. Nice stretch. You're awake now. Good. I want you to think about the potential difference, the voltage, as the height of an object. Boy, my pen was kicking in and out there. Let's try that again. And the amount of charge that has been separated in coulombs, that's like the mass of the object that's been lifted. So it's possible, Mason, if I dropped a ping pong ball on your head from the ceiling, meh. Where if I dropped a bowling ball on your head from the ceiling, ouch, we would say both of those would have the same voltage. One of them would have a stronger current. And this is why we say when we're talking about a circuit, it's the current that kills you, not the voltage. When Katie and I think Mason, I think it was the two of you that getting shocked, yeah? And Matt, when the two of you were getting shocked, you were actually putting probably about 25,000 volts, but almost no current. Very, very little current, enough to make you go ouch. Here would be the analogy. Voltage is like the height. If a raindrop, a single raindrop falls on you from a great height, will that single raindrop do any damage to you whatsoever? No. That's like what you guys were getting from the Van de Graaff generator. Current is like how much water. So if I dropped a swimming pool on you from ceiling height, would that, not the pool itself, but the water in the pool, would that probably do damage to you? Even though it's not a high voltage, it's a high current, that would get your attention. Oh, and of course, the worst would be dropping a swimming pool from a very, very high height, high voltage and high current. That's going to do lots of damage. Okay? We'll talk about that more. So electrical energy, the amount of energy in a battery, depends both on the voltage and the amount of charge separated. So, I have some batteries here. Nick, here's one for you. Christian, here's one for you. Matt, here's one for you. Here's one for you. 1.5. And, I got a big one here too. Well, Brady, you already read this one. Brady, that is a big C battery. Can you hold it up nice and high so everyone can see? What's the voltage on that? 1.5 volts. So yours is smaller. It must have less than 1.5 volts, right? No, what?
Yeah, it's 1.5.
1.5 volts as well?
Yeah.
Oh, yours is smaller. Yours must have less than 1.5 volts, right?
No.
What? 1.5 volts as well? How about...
Yes.
Really? No. This is how they're made. It's the same chemical reaction going on in each of these batteries. They are the same voltage. Now here's the question. Think about this. Which battery do you think would last longer? Which one has more electrons? Okay, yours would last longer, so Mr. Dewitt, why don't we put those into every one of our electric devices? Because we want our toys to be smaller. Right? I mean, that's the trend with electric devices. We want to make them thin, we want to make them small, and so we're trying to find ways of creating the same voltage. The battery won't last as long. You know what? We'll get you guys in the habit of charging up your batteries every night. Hey, that'll work. Which most of you do, I think. Yes? Okay. Now, these are a different style and a different type of battery, but I don't know if you ever noticed, this voltage, does yours also say 1.5 or does it say anything on there at all? 1.5 volts, this is a 4A battery, not very common. Here is a D cell, a C cell, AA, AAA, single A's, which are very rare for some reason, but they do make them. This is a 4A battery. This is what has to be used in my little pen that I write with on my tablet PC. They're all the same chemical reaction. They all have the same voltage. How many volts? 1.5. How many volts? Ready, 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 ready? How many volts? 3. 3. Okay? What if I put this together with another one of these? If I had 4 of these in a row, how many volts? If you buy a 6-volt battery, I'm telling you, all it is 4 of these linked inside that. If you take that, don't take that battery apart without eye protection and gloves. But if you take those 6-volt ones, are those kind of rectangular ones that they use for flashlights, take it apart and you'll see there's 4 cells in there, 1.5 volts each. Or we have the rectangular batteries, the ones with the 2 terminals on top, 9-volt batteries. You'll also notice that 9 divided by 1.5 is 6. There's 6 cells in a 9-volt battery. And a car battery is 12 volts. You can go 12 divided by 1.5, and you can see how many of these, it's a different chemical reaction, but the same idea, are in a car battery. I don't know if you ever wondered why voltages are all multiples of 1.5, and they are. It's because of this chemical reaction here. Hashtag nerd trivia. So, in our notes, AA or AAA, have you ever looked at both a AA and a AAA battery? We just did. If you read the battery, you'll find they're both how many volts? So, what's the difference between them? Well, a AA battery is larger than a AAA battery, so it separates more charge, and so lasts longer. Why then would you want AAA batteries and not AA batteries? Pardon me? Yeah. We like our tech small. Smaller the better. Okay. But the consequence of that is you'll probably have to replace those batteries more often. Or what they'll do is they'll set the batteries up in parallel, and we'll talk about what that means when we start looking at circuits. So there is a way that I could have 2 of these side by side, which is still giving me a total of 1.5 volts, but this is supplying half the charge, and this is supplying half the charge, and I'll get twice the length, twice the lasting out of these. So if you ever look at a remote control, notice whether the batteries touch like this or are side by side. If they touch like this, that remote needs 3 volts, and here's an easy way to get 3 volts. If they're side by side, they've set up this remote control so that the batteries will last twice as long because you're only using each of them to power half the remote, basically. That's not quite right, but it's a pretty good analogy. Next time you change your batteries and device, look inside and see how they're set up. D cells. That was these big boys. They also carry a potential difference of 1.5 volts. How is this different? Bigger. So what does that mean? Why? It contains more charge, more extra charge. Okay? So how is it different? Contains, I don't know if I had this in your notes or not, more charge. So when would a D cell be useful? If you're using a device that you don't, the classic is a flashlight, because most flashlights we want actually not to be too thin. We want them to be about the thickness of our grip. Hey, this is almost perfect. We'll use either D cells or C cells in most flashlights, especially the big industrial mag lights. The ones that, the life and death rescue flashlights, not the cheap one you keep in your glove compartment or the cheap one you keep in a kitchen drawer, but the one that I need to work out in the wilderness if I'm by myself and I want it to last for a long, long time. Do I have this in your notes? When would a D cell be useful? When we need something to last longer and the size of the object isn't that big an issue. I guess I should say when the size or the mass of an object. You probably wouldn't want those D cells to try powering a little remote control helicopter, for example, because the weight of those would make the helicopter not be able to take off. So far, so good? All of these columns of water are the same height, therefore the same voltage. 3 pictures, 1, 2, 3. Just like a AAA, AA, and D size battery are all 1.5 volts. Which one of these has more stored energy? The one on the left, the one on the right. I have to reverse everything. One on the right for you guys, yes? The height difference makes up the voltage. They're all the same height. The amount of water in the column changes the total energy, how long the battery will last, but not the voltage. Is that okay? So, how do we produce voltage? There's 2 main types of electrochemical batteries. Electrochemical cells. Pardon me? There are what we call wet batteries and dry batteries. Your car battery, if you ever looked at a car battery, it's typically considered a wet battery. In fact, your battery, depending on how old it is or the model, if you look at the car battery, you may actually have to add water every so often. There might be a little plastic lid that you can pop off, and you literally pour water in there. Okay? They're using the water as part of the way to conduct electricity to send the electrons from one terminal to the other. Dry batteries technically aren't dry. It's just that there's not a liquid inside. There's a paste, usually an acid paste inside. Dry batteries are these things. There's no liquid in them. Really what we mean is this. Trevor, a dry battery, I can install it like this, or like I can install it upside down, no problem. Wet batteries have to be kept right side up because stuff could pour out, and if they pour out and become dry, then fire bad. Wet batteries, typically car batteries or boat batteries. In boat batteries, it's a bit of an issue because boats move back and forth in the waves, and so you'll see you have to be very, very careful with a boat battery to make sure that you don't accidentally flip the battery over. That's not a good thing. Or you might pay for a more expensive version of your boat battery that's completely sealed, and that way if it tips over, Matt, you're going to make it. That's a long blink. I know I've been talking for a while. Then you won't spill the liquid out. An electrochemical cell needs 2 electrodes, usually metal, and an electrolyte which will allow electrons to flow between them in a controlled manner. In a dry cell, the electrolyte is actually a moist, pasty thing. Usually acid, but sometimes it can be spell that right, Mr. Duick. Alkaline. But you may have heard the term, Mason, battery acid. That they're talking about the paste inside the battery. You don't want that to get on your skin. It wouldn't like eat a hole in you, but if you left it on there, probably in 30 seconds or so, you'd have a mild burn. So, in a wet cell, the electrolyte is a fluid, often water. Once you've written that down, put your pencils down. A couple of videos to show you. I've been talking a lot, I know. So, more thoughts. Chemical reactions. So here is a very, very basic battery. Not a good one, but we will actually get a voltage here. We have a copper electrode and a zinc electrode, very similar to the video we just watched where we put a zinc nail and a copper wire into a lemon. Chemical reactions take place. The copper wants electrons more. It has a higher electron affinity than the zinc does. So relative to the zinc, the copper is positively charged because it wants electrons more, and because unlike attract. Okay? Chemical reactions take place that a remove electrons from the copper strip leaving it with a positive charge, and actually remove atoms from the zinc strip. In fact, the zinc strip would look like it was rusting slowly, getting more and more brittle. It would look like it was decaying because atoms are leaching into this solution here, leaving electrons behind, which is negative. This creates a potential difference and is the basis of a battery. You now have two differently charged sections. What we need is a breakthrough in battery technology. We're pretty good. But how long does it take to charge up your smartphones? Instant? Why can't it be instant? We're working on that. We're working on the ability to charge batteries up pretty instantly, and the ability to store more charge, and the ability to recharge over and over and over. Now, we've already made huge improvements. When I was your age, when I was in high school, rechargeable batteries sucked. They're terrible. You could maybe recharge them 40 or 50 times, but each time you recharged them, they would be able to hold less charge. And these were the old type that if you didn't completely drain them, they'd develop a memory and they'd only go down as far as you let it go before you recharged it. They were terrible. In fact, I remember when I was in high school, my physics teacher told me at UBC they're working on these lithium batteries that I think these could really make a big difference. They'd be a way better way to have rechargeable batteries. That's what all of you have in your devices and your electric toys. Those are lithium-ion rechargeable batteries. They can be recharged 900 to 1,000 times. They don't have that memory. You can leave them plugged in. On the old ones, as soon as they got charged full, you had to take them out, otherwise you could damage them, or you can leave your phone plugged in overnight and it's not a problem. So we've gotten much better, but we want to get better yet. Put your pencils down. So we're hoping for bigger, better batteries. We will pick up after your test to see how much of this you remember. I'm going to have some questions. We'll answer them orally, so your homework is to study.